Hello everyone, I hope you're well. So today I'm presenting a little bit of the work that we are developing in Australia at QUT, Queensland University of Technology, with Associate Professor Veronica Garcia Hansen and Dr. Gillian Isuardi from Leonard. And as Mandana just mentioned, it's about the dynamics of the view, or how we see the views outside the movement that we see from the windows. We're calling it exploring the dynamics of window views, and we are trying to integrate image-based analysis with self-reported assessment. So views in the context of low carbon, high comfort integrated lighting, we know that views, of course, are important for well-being and for health, right? So there's a lot of evidence and research about that in environmental psychology or in health studies, but it's also relevant to the understanding of conditions within the building. So, for example, we know that visually complex outdoor scenes can reduce our discomfort glare, so we can have less glare if the view is of certain quality. And we also know that pleasing natural views can enhance individual thermal quality. So we tend to be more comfortable with our temperature if the view outside is pleasing to us. So we are thinking as a group, like, what attributes contribute to view quality, and that's how we contribute also to the task. How can we understand the quality of the view? And from the point where we come is through understanding the dynamic of the outdoor. So thinking of, there are different aspects of view quality, view acuity, view clarity, right? So there are view content as well. But we are interested in knowing what happens when time changes, and because windows can give a lot of information about the world outdoors, right? Mandana was just mentioning, we spend 90% of the time indoors, and the rest of the time, our connection to the outdoors comes through windows. So, and there is a lot of research now in terms of organizational psychology that understand well-being, the processes of well-being. So well-being as a dynamic construct that happens over time. So we tend to, at work, for example, there are times that we are more productive, times that we are less productive. So this changes as the day progresses. And there are some studies that we have been working on, and we are interested to mapping how the outdoor changes and how can we bring this as a descriptor for view quality. We have done some preliminary work in this aspect. So we have used semantic segmentation, which is from computer vision, to define different labels within a view. So understanding how a view, the content of a view can be systematized in a way. And then we have used MATLAB or more programming approaches to define absolute variation in the converting images from RGB to LAB to understand more of the absolute change in the lightness channel. So we can, comparing images over specific consecutive time lapse, we can have an understanding of the change over time. So what you could see, for example, to your right is the assessment of lightness over consecutive time intervals. So we can map how much the lightness change. Of course, it's just one channel. And we use a combination of tools. We use cameras, of course, and 360 time-lapse video cameras under different sky conditions to map this out. Working. So this is the same view as you see. This was taken over a day, but this is just 20-minute footage of what you see. And of course, if people is just presented with a picture of the view and then asked to respond, what's the quality of this view, they would just see a picture. But we know that outdoors is not static, it's dynamic. So that's what we're interested to know. And this is an example of how the lightness changes across the day. So in one, of course, you can perceive more variation, and on the other, you perceive a little less. There's always variation, of course, but what you perceive is less of variation. So the way we were testing this is through VR. So we use VR to testing this because VR and the 360 cameras allow us to present people with the same stimuli over time. So we can compare, we could compare different, and this was part of an experiment we did some time ago in Australia with 48 participants. We used an adaptation to the perceived restorativeness scale, which is one scale used to address attention restoration indoors. And that's something that we're also working with the subtask is on the understanding the questionnaires or how to systematize a little bit of this questionnaire. So these are the questions, and yes, we did the VR with people. They were rating with a score 1 to 5 how they prefer or how did they think of the views. And if you see, we put some questions in between addressing specifically prediction of change. So do you think this scene will change, or how you can see variation in this view, in this window view? So at the moment we had up until now this objective assessment that comes from the image-based analysis. And on the other hand, we have the subjective assessment coming from the VR experience. So in the VR, we understood that yes, people tend to prefer views that present some variability over views that they don't present variability. But what we didn't know is how, if the image-based analysis could be contrasted with human surveys. So we had from one hand the images, and the other hand we had the VR, but we didn't see how these two could be linked. And the aim that we are trying to, with these studies that we're conducting as part of this task, is to understand how to combine these two, or if it's possible to combine these two. And we find some approaches. This is still work in progress, of course, and I'll show you this now. So how to analyze these two things in a combined way. The first way we are approaching is through causing similarity. This is again from mathematics or computer science. It's a metric that measures the similarity between two vectors in a multi-dimensional space. So we could think of a picture as a two-dimensional space. And then we could see, as in the graph here, you could see all the pictures that are when they have a 1, that means there is no variation between two pictures. It's the same picture compared against itself. But as the time progresses, you can have, as in the pictures here, you can have comparisons between different points in time. And that will give you an idea, an estimate of the variation over time. So we could compare images at different points in time and see how much this varies, okay? So across a whole data set, if we have an hour of or a full week of videos, that's something we can compare how lighting changes. And the other approach is also common in computer science, is the regions of interest or the cluster of variation, in our case for the L channel or the lightness channel in the LAB space model. And it's to understand a specific area within an image that can present features that serve for recognition, okay? So the issue that we have in view research most of the time is that we all use different descriptors to views. We think we analyze building versus nature, or distance, close to far away, water versus greenery. So there is a whole set of descriptors that are all very relevant, but we need to come to with a systematized way to analyzing those. And by using a more systematic approach, we could use different categories to present this. And that will give us an idea of what in the scene changes. When you're seeing just a picture, what is the aspect that is bringing up more variation. So this is how we have been testing the approach. What I'm going to be showing you is still work in practice. We started to combine these two, we started with the responses from this VR experiment. So we selected 3 questions, as I mentioned before, that address variability. We had a sample of 320 video samples from which people scored high and low to variation. So we use the scale to see when people is saying this scene varies a lot, or when people say this scene doesn't vary at all, so this video doesn't vary. So we use some scores, so under 2, that means that's a low variation, and over 4, in a scale of 1 to 5, that's high variation. So the scene that you see here, I'll show you in a minute, that's a highly variating scene, and the other one is a low variation scene. So we use cosine similarity for 32 videos of 21 frames each, so that's representative of 20 minutes of footage. And the region of interest, we use 3 descriptors here: porous for the nature and greenery, non-porous for the buildings, and sky. Of course, this can be changed. It depends on how you approach. That's something you have to discuss. The code was made, is still a draft because I need to adjust to make it usable for people. It will be available as part of the deliverables, and will be also available in GitHub for everyone to use. This is a cosine similarity, as you see. The one is the no changes, and this is a scene that people said it changes a lot. I know it's small, the picture, but we could see in the image, perceive some change in the from point 1 up to point 10. We see that there is a change. However, we see that there is no significant change in the image. So people is perceiving that some change, but the image is telling you there is not so much change in here. So just taking this sample of something that perceptually varies. So in this case, the T1 to 18, who was it's just 0.98, so it's very low. So we tend to see more variation there. On the other hand, this one here, people said this scene doesn't vary too much from T4 to T7, but it varies even more than the previous one. So that's something interesting to start considering when it comes to this. And then when we see the region of interest, this is a high score variation scene. We divided these three. We mask the different aspects within the room. So the code disregards all the 0. And we see that the variation is very high in nature. Nature is the one that varies the most. And buildings, they vary somehow, and the sky also varies. So they all vary in similar patterns. It doesn't vary one over the other. However, in the other scene, the scene that presents low scores for variability, the variation is still very high, especially for nature. When it comes for the non-porous or the buildings, it varies also quite significantly, even though people say it doesn't. But the sky varies very, very, very little. So, so this is just one example, but what we are seeing is that whenever the sky presents some change is when people is more keen to say this scene is varying or significant. So this is my final slide, cosine similarity. We are seeing that perceive high variation. People perceive a lot of variation, but the variability range are low. That's expectable because the picture is taken from a static point of view. Views with high variation and scored low present little presence of sky, and also, so basically the sky seems to be a quite significant component here. In terms of the region of interest, variation occurs in similar proportions, and greenery greatly varies across the sample. So it could be interesting to see this as we tend to think, yes, nature is relevant in this assessment of views. But maybe it's not just the green index that we need to look at, it's also the movement that it produces that is bringing something related to the preference of that view. And the sky descriptor correlates with scores of variations of the more. Finally, the code, we will be making it accessible and will be able to be used with different descriptors. Will allow for, with disregard some mask fits. Of course, it's open to improvements. And some limitations and work in progress. Of course, at the moment, we're just using the L channel, but we can include other aspects of the code or use a different approach, as we were seeing in the presentations yesterday with the LBNL group. It's using VR, but could be addressing naturalistic or field studies. We don't know where people is looking at, so we could approach this with an eye tracking approach to see, okay, if people is looking at specific points in the scene, And also finally tying up with the non-visual effect, if sky is so relevant, can similar or more approaches related to this help us understand the non-visual effects. So using camera for things horizontally, different color spaces or different heights. Yeah, that's in a nutshell. Thank you.